Hey everyone, welcome. So exams are right around the corner, and I know electrochemistry can feel like a tough one. But seriously, don't worry. Today we're gonna blast through the whole chapter with a super fast revision, and I'll be sharing all the best tricks to help you absolutely nail it.
Look, a lot of people think this chapter is difficult, but it's not. It's just really logical. And I promise, after we're done here, it's going to feel so much simpler. We're going to cover tricks you can use directly in your NEET, CBSE, and ISC exams. Ready? Okay, let's just dive right in.
All right, let's kick things off with the absolute fundamentals. What even is an electrochemical cell? Well, to put it simply, it's just a cool little device that turns chemical energy into electrical energy. And the most common example, the one you'll see everywhere, is the galvanic cell. Now this right here, this is probably the biggest, most important trick in the entire chapter. If you only remember one thing today, make it this: anox, red cat. It's so simple. Oxidation happens at the anode, that's anox, and reduction happens at the cathode, red cat. Simple as that. So let's break that down just a little more. For anox, you've got oxidation at the anode, and remember, the anode is negatively charged. For red cat, you have reduction at the cathode, which is positively charged. You have to lock this in because this exact concept is a classic previous year's question. NEET loves to ask where oxidation happens. Let's apply this to a real example, the Daniell cell. Here's a super easy way to remember what's going on. Zinc loses, copper chooses. Zinc is the one that loses electrons, right? So it gets oxidized. And copper? Well, it chooses to take those electrons, so it gets reduced. See? Super easy to remember. So this begs the question, which way do the electrons flow? It's just plain common sense, really. Electrons are going to flow from where they're being given away to where they're needed. So the key takeaway is this: the flow is always from the anode to the cathode. This is another one of NEET's favorite questions, so don't forget it. Okay, let's get into the mathy part of the chapter. But don't worry, we've got tricks to make this easy too. We're going to talk electrode potential, EMF, and the big one, the Nernst equation. All right, here's a pro tip. Whenever a question gives you a bunch of values, the first thing you should look for is the standard reduction potential, or SRP. That's your key. It's simple. The substance with the higher SRP is a better oxidizing agent, and the one with the lower SRP, well, that's your better reducing agent. You're definitely going to find comparison questions like this on your exams. And here we have one of the easiest formulas for grabbing marks. To calculate the standard EMF of a cell, or E0 cell, the trick is just remembering this: always cathode minus anode. You literally just subtract the anode's reduction potential from the cathode's. This formula is a guaranteed question year after year, so it's basically free points. And here it is, the famous Nernst equation. You guys, this one is so important. We use it when we're not at standard conditions, like when the concentration isn't 1 molar. Now, for your calculations, the key thing to remember is that magic number, 0.0591 divided by N. That's your go-to when the temperature is 25 degrees Celsius. So let's build on what we know. We can actually connect all this cell potential stuff to thermodynamics. In other words, how do we use that E0 cell value we just calculated to figure out if a reaction will just happen on its own? You know, if it's spontaneous. And for that, we have what I call the golden triangle trick. Just think of delta G, E0, and K as the three best friends. Why? Because they're all connected. If you know one of them, you can always find the other two. This little relationship is used all the time in exams to check if a reaction is spontaneous. Okay, let's switch gears. Up until now, we've talked about cells that make electricity. Now we're going to flip that completely. We're diving into electrolysis, where we actually use electricity to force a chemical reaction to happen. And this slide lays out the difference perfectly. A galvanic cell, that's spontaneous. It takes chemical energy and turns it into electrical energy. Electrolysis is the total opposite. It's non-spontaneous, and you're using electrical energy to make a chemical reaction happen. Now for Faraday's laws. They sound way more complicated than they are. You can boil them down to two simple ideas. The first law is basically more charge, more mass. The amount of stuff you deposit is directly proportional to the charge you run through it. The second law tells us that equivalent weight matters. The mass you get also depends on what substance you're using. These are huge for numerical problems on exams. All right, on to the next section. Now we're going to get into how well different solutions can actually conduct electricity. This is all about how ions move around.
The easiest way to think about this is with an analogy. Resistance is like a roadblock. It stops the flow of current. Conductance, on the other hand, is like the open road. It helps the flow. It's really that simple. Conductance is just the inverse of resistance.
Now, here's a part that can be a little tricky but is a super common exam question. What happens when you dilute a solution? Well, the specific conductance actually decreases. Why? Because you have fewer ions in the same amount of space. But, and this is the important part, the molar conductance always increases with dilution. This trend is a favorite for graph-based questions. So how do we figure out the conductance for certain electrolytes? That's where Kohlrausch's law comes to the rescue. The trick is right in the name, independent ion migration. It just means that when a solution is super dilute, all the ions are so far apart that they act independently. So the total conductance is just the sum of all the individual ion conductances. It's incredibly useful.
All right, we are on the home stretch now. We're going to finish up by looking at some real-world applications, batteries, and then we'll do a final, lightning-fast recap of everything we've covered.
For your exams, you don't need to be a battery expert, but you do need these quick facts. First, the lead storage battery. Just think of it as the heart of the car. You need to know the anode is lead, cathode is lead dioxide, and the electrolyte is sulfuric acid. Then there's the fuel cell, which is all about green energy. Its reactants are just hydrogen and oxygen, and its only product is water, which is why it's so environmentally friendly, a key point for exams.
So let's just take a step back and see how this whole chapter flows. It's a logical story, right? We start with the basic cell, then we figure out its standard EMF, or E0, then we use the Nernst equation to account for concentration and check spontaneity with delta G. From there, we flip to electrolysis and Faraday's laws, then talk conductance, and finally, we end with a real-world application, batteries. See? It all connects.
And last but not least, here is your cheat sheet. This is the golden list. Looking at the exams from the past 5 years, these are the topics that come up again and again and again. So if you're short on time, this is where you focus your energy. Master the Nernst equation, EMF calculations, and all these other concepts, and you'll be in great shape.
So what do you think? Are you ready to crack electrochemistry? I really think you are. You've got all the tricks and the core concepts right here. The only thing left is for you to put it into action. So go on, solve some problems, practice, and you are going to absolutely ace this chapter.